Yeah, good morning. Let us resume our discussion. So what were we discussing in the last class? Any couple of points? So what were we discussing in the last class? I suggest any of you quickly brief a couple of points on the last class. We will move on to the discussion on the subsequent topics today. So none of you were there in the last class on Monday?
We were discussing about different types of resolution and how RGB channel works.
Right. Okay, fine, good. So what else? What else were we discussing in the last class? Didn't we discuss what is computer vision? Briefly?
Yes.
Yes. Okay. So let's resume our discussion. So we define computer vision as the ability to impart the knowledge of inference or vision to the computer through the pictures or videos taken from the camera. So essentially, after a basic understanding of computer vision, we started looking at what's an image or how image is looked at by a computer. The way the humans look at an image is completely different from the computer looks at an image. So we were trying to understand what computer looks at as an image. So we have seen a grayscale image on the left side and then RGB image here on the right side. And we have taken a small patch in the image and trying to understand how the computer looks at it. So it looks at it as a matrix or set of intensity values, two-dimensional array of intensity values. So then we started understanding what is the spatial resolution in terms of what is pixel resolution. So for a given camera, we said it can be 10 megapixel camera or 1 megapixel camera and so on. And based on the number of CCD sensors a camera has or CMOS sensors the camera has, we define its pixel resolution. And each sensor element, how much region does it look at the physical space, that defines the spatial resolution. That maps based on the field of view of the camera. It will meet sensor element how much square area it looks at the real world, that we consider as spatial resolution. And then we also discussed about the photometric resolution or intensity resolution. Once we capture the image of a scene in terms of the intensity variation at different locations of the scene, what each sensor element looks at is nothing but a small region in space. So it may be looking at a small region. First sensor element here may be looking at this much small region. Similarly, the camera sensor element here may be looking at this much small region in the space. What it does is it makes the average intensity, average brightness, and the reflectance of it is measured in terms of intensity, and that is quantified in a range either 0 to 255 or 0 to 1023 and so on, based on the intensity resolution these sensor elements has. So it can be 8-bit resolution or it can be 10-bit resolution and so on, that we discussed in the last class. Usually it is 0 to 8 0 to 8 bits or 8-bit resolution. So we consider it the intensity values ranging from 0 to 255. So what happens if we take a picture is essentially each of the region in space is encoded in terms of 0 to 255 values or the intensity values at the corresponding location or corresponding sensor element. And that we can see as visualized as a 2D array of matrix describing the scene in terms of an image. Okay, so now given this information of a matrix of matrix or elements of intensity variations across the scene, what we would like to see is understand say where say what object is there at a given location, or where are the intensity variations in the scene, or what is happening in the scene, based on, or what is the 3D structure behind this 3D reconstruction of the scene behind the image, or from the image that is taken. So all these we would like to infer from the matrix of elements that we have. So are the intensity variations of the scene that we capture through the camera. So that's where the challenge lies. So the computer sees it as a matrix of elements of intensities, whereas the human inference needs objects, persons, movement, okay, and then many other things. So now the question is on how do we infer it, or what methods has to do for getting these inferences. We also are quite familiar with the RGB images, and we have seen that in RGB, like red, green, and blue, are 3 different channels in the image. So instead of a grayscale image where you have a single matrix of 2D array of intensity variations or values, you have now 3 2D arrays. So it's like a 3 channels of the 2D arrays, or 3-dimensional arrangement of 2-dimensional matrix channels of red, blue, and green. Okay, so and you can see clearly that what red channel highlights is nothing but the red regions. Of course, white will be there in all of them, because as you know, white has equal proportion of R and G and B. So there is a good reason for considering RGB channels compared to any other intensity variations in WebGR that is closely tied to the visual perception. In fact, the cameras are also modeled so based on the visual perception to capture the color variations well with R, G, and B filters. So you can see here in the R channel, it highlights the red region. In the say green, by looking at the channel itself or the image itself, you can tell which are bright in say which are more bright in green, which will be more bright in green, which will be more bright in red, and so on. Okay, so there are different other representations of the color images based on the problem that we would like to tackle. For example, if you would like to see RGB channels, it's more of in different color bands how the image looks at. So in some cases, we want to consider the overall intensity as one channel, and then the other variations other than the intensity, like hue and saturation, may be other in other channels, or YCBCR is other way of representation, where Y again represents roughly a average intensity variations, and CBCR are chrominance and luminance kind of chrominance components, 2 different chrominance components. So based on how we would like to visualize an image, different representations for the color images are done. Essentially, the problem in image processing is to take an image as an input, and then process and provide a image that is visually appealing or more useful for the subsequent higher level task as the output. As we discussed in the previous lecture, the aim of image processing is to take an image and give a output as the processed image. It is also considered usually as multidimensional signal processing, because the 2-dimensional signal is considered as an image. So broadly speaking, image can also be considered as signal, because any signal, a broader definition of signal encompasses finding out like having a varying quantity, either time varying or spatially varying quantity, and then it has information in it. So information bearing time varying or spatially varying quantity. Of course, the specific definition of signal also comes with the system that is attached to it. It should describe a system, then only it can be considered as signal. If we strictly consider signal as a connected outcome of the system. But however, signal also can be considered from the man-made systems, describing the man-made like from the man-made signals, but describing the natural phenomena. So under that consideration or definition, we can consider image as a 2-dimensional signal. So it has a spatially varying nature. The variations of this describe the natural variations that are underlying natural variations, and it has the variations in both x and y direction. And also it describes the natural phenomena of either objects or movement of objects and so on. However, it's given by the custom or man-made device of camera. So the image processing, if we purely discuss on an image processing course, it has more component on processing aspects. So wherein we would like to see so how different kinds of processing can be done in an image. Say for example, usually the images itself comes with noise when we take with some of the sensors or under some circumstances. So if we take a satellite image, for example, we cannot make an image without noise or free from noise at the beginning itself. It will obviously be corrupted with noise. So how do we make it free from noise is a challenging task. Similarly, medical images are also corrupted by noise usually based on the device characteristics. How do we free or how do we restore the image from the noise is one of the important image processing tasks. Similarly, there are other image processing tasks that are of interest. These image processing tasks are also important for subsequent inference tasks. So we will discuss even in computer vision course some details of processing, image processing, and that we consider as some kind of pre-processing. Usually a computer vision task, or if you would like to make an inference, we cannot directly make an inference. First, we have to make a kind of processing, and then we have to bring in a little bit of attributes to that processed image or attributes to the object of interest, and from then we should be able to make inferences. Say just an example. So if you would like to make this from this image, now our aim is not to process, but we would like to infer how many razors are here. So how do we do that? Say if you would like to count the number of razors here. So any guess on how do we proceed? Say if we would like to make just make a counting of how many razors are here in an automated way through the computer. As you know now, this is nothing but a matrix of elements for a computer. And from that matrix of elements or matrix of intensity variations or a matrix of intensity values, we should be able to find out the number of razors here. Also, any suggestions or thoughts on how do we proceed to the next step, or what should be the first step? Any quick thoughts are welcome.
Sir, canny edge detection we can use.
Okay, that's fine. So essentially you can use canny or whatever edge detection you are saying. So what do we mean by edge detection? And what is it useful for?
Is it like sharp changes in intensities?
Very good. So essentially edge detection, edges are nothing but the sharp transitions of intensities. Say for example, if we essentially consider a one-dimensional signal, then where we say are the transitions occur in a one-dimensional signal? If we have a one-dimensional signal, okay, where do you think we can attribute the transitions to? So where do we see that? Say, how do I find the transitions automatically otherwise in a one-dimensional signal? Can say assume that I would like to make a automated process for identifying the transitions in a one-dimensional signal. Okay, one-dimensional signal means, say there is a you can assume currently it might have come from a system or it may be a measurement of some process. Okay, but we assume that there is a sequence of numbers that are going. Okay, in a sequence of numbers, I want to know where the sudden transition has happened. What do you think is the procedure that can I can easily apply or figure it out? Or
we'll first try to look at the whole array and see what is the average changes from one point to other, and then again see where there are more than the average value.
Right, very good. So what we do is here, if I have plotted a one-dimensional signal, so let it be whatever signal. It can be a current or voltage signal, or it can be any speed signal, or it can be any variations of the with respect to the time. So now if you want to find out sudden transitions, you can easily note that the sudden transition has occurred okay, in this region. Is it not? So you can note the certain transition. How do we algorithmically find that? Is how do we algorithmically find out the differences between consecutive samples. Say, just to give a simplified solution. So we can find out the variations with the consecutive samples. That is, say, if we consider this the x of say t is the signal, if we assume x of t minus x of say t minus delta t or t plus delta t. Okay, we can find this. This is, we consider it as the, say, if I consider a different signal, okay, wherever this difference is higher than some threshold, we can consider it as a change, okay, or a sudden change or transition. Okay, similarly, in images, we do exactly the same thing. Say, if we bring this to a discrete world, so then how should the variations can be found? Say, in a discrete signal, for example, now if I want to do the same, I want to find out the variations in a discrete signal, then what can we do? Say, I want to define as d of n now for a discrete signal x of n, and then where the variations are higher, at that locations x of n minus x of n minus 1 may be higher or will be higher. Is it not? Or x of n plus 1 minus x of n can also be higher. Is it not? So this is how wherever d of n is greater than threshold, we say that there is a there are either variations or transitions. Okay. So similarly, those transitions on in images are referred to as edges. Okay, so we will see more specifically the definition of edges or how do we find edges. For now, we assume that wherever there is a sudden transition of intensities, there are edges. Okay, so since it is a two-dimensional thing, okay, transition has to be measured both in x direction and in y direction. Okay, so since we measure both in both directions, then the variation like x in x and y also is counted. So essentially dx, okay, variation in x, and dy is counted, and then our gradient in x and gradient in y are considered, first computed, and then the overall variation can be obtained by dx square plus dy square or something like this. Okay, so this essentially provides us the high gradient or high variation regions, and if I threshold it, I can get the edges. So assume that I have got the edges here. Okay, and what does these edges finally describe? So after getting edges, okay, that's fine, but what these edges describe in this image or in general in any image? Any guess on it? Yeah, please.
Boundaries of different objects.
Very good. So they describe the boundaries of different objects. You can see that the boundary of this object is the edge corresponding to it. Similarly for all. So now, very good. So we can use the edges to find out the number of edges. Assume that I have found the edges. Up to finding edges, I consider it as a pre-processing or an image processing task. Okay, because this is a the input is an image and output is also an image. Binary image in this case, because I have thresholded. More than a threshold, I considered the gradient. More than a threshold, I considered as edge. Less than a threshold, I put 0 there. Okay, without having an edge, no edge. Okay, so now after performing this pre-processing, what do you think is the next step to count the number of edges here? What do you think is the next step? I have the edge image here. After that, what should I do with this?
Group those edges, see any meaning is there on.
Okay, fine, very good. So assume that I have grouped the edges. I have somehow found, see that's usually called in image processing as connected components. So what I do is, if there is a connection, I make that this whole thing is a single connected component, okay, of an edge. Okay, so as when there is a break, I consider it as a different object. Okay, till there is a break, it is the same object. Fine, that's okay. Somehow I grouped and made some edges, like some connected components in edges. Okay, after that, what do you think I will do? What do you think is the next step? We need to find out the number of edges here. Okay, after this, what do you think is the next step? So I have got roughly edges like this. No guess? Okay, so what essentially I need to do is I need to find out where this kind of objects are. Okay, so I take a template of the razor. Fine, I take a template of the razor, and then what do I do with the template of the razor? Template of the razor means a template of the edges of the razor. Okay, and after that, what do I do? What do you think we will do? We take this template, and then what do? We will
Compare with
we'll compare with, say, roughly this is the template I consider. Okay, and then I start comparing it. So, but the problem is, see this, you assume that this is 100 cross or 200 cross 100 image. Okay, so there are 200 cross 100 means 200 columns and 100 rows here based on the arrangement that we have here. So 100 rows and 200 columns. Okay, so and then this is roughly assume that, say, it is maybe so 20 cross 10 or 25 cross 20. Okay, so now I want to compare at each location. I want to find out the number of razors present. Okay, so how many comparisons should I do? How many comparisons do you think that I need to do to find out the razors in this image from the edge image? How many? Any guess? Say it is 100 cross 200 image. Okay, and then we have roughly the size is given. First of all, how many locations should I compare for identifying the razors? Yeah, quick answers are welcome. At how many locations should I compare this? See, razor, should it be pertaining only, should it be there only at this location? Or can it be there at any location?
at any location.
Yeah, so how many comparisons or how many places should I put this razor and compare? The template and compare.
Approximately 200 into 100.
Right, approximately I should I should compare. Okay, at 2 into 10 power 4. Okay, places. Fine. And but the problem with this is, what do you think is the problem with this? If I compare, is it enough to compare it to 2 into 10 power 4 locations with this razor template, and then will I be able to identify all the razors present?
No, sir, because sizes can be different and there can be a tilt in the razor also, angle.
Okay, so sizes can be different and there can be rotation. Okay, and what else? Do you think still there may be problems in while comparing?
There can be overlapping.
There can be overlapping, occlusion it is called. Okay, and for partially visible and so on. Given all these things, you require, say, large number of computations even to compare and find out, okay, the number of razors in a image. You see how simple task for us is how difficult for a computer to do, if we naively try to do it. So this is where the computer vision has started. So making inference from images is not very simple, because the objects may appear at different scales, different views, different rotations, and different maybe occluded, okay, and many other variations. Intensity variations, we have not counted for intensity variation set. So if I ask a question of how many razors are black razors here, okay, some such questions, it will be even more difficult. Okay, so all these bring in a lot of challenge for developing the computer vision methods. However, the usual computer vision methods has a pipeline of pre-processing and then kind of inference. See, the one kind of inference I can make is, somehow I can see that if it is a razor, say I may have different, I have made a template here with 5, here 5, I can consider it as the width and this as the length. So 20 cross 5 as the razor blade size. Okay, in that case, there may be some other object which is of a different size. Okay, so these attributes, if I start finding, I directly find out somehow, okay, all the razor blades, okay, the rectangular boxes corresponding to razor blades. From the edges, I directly find out somehow the rectangular boxes corresponding to razor blades. Once I find it, I may use the attributes of it to easily identify whether it is a razor or not. So there, those are referred to as feature extraction or finding out the attributes. And then with the attributes, I make later an inference saying that whether it is a razor or not. So essentially, typically, pre-processing, feature extraction, and then either classification or high-level inference is usually done in many of the computer vision tasks. Okay, so that's what you see here in this slide. So we start with pre-processing. See, here is another example. What we want to perform here is an automatic classification of the fishes coming on a conveyor belt. See, we will see in the next slide the definitions of different courses that are very similar or that has some overlap. Say ranging from artificial intelligence, image processing, machine vision, computer vision, okay, and related courses, other courses. So we essentially, when we want to apply the computer vision has, the name is given because the computer has to be imparted a processing or algorithmic capability to infer from images. So that's where the computer vision, term specifically computer vision refers to. Machine vision refers to bringing it in automation, more like automation. So either let it be in the in the industry setting, or even there is other term called robotic vision, where especially if we bring in kind of inference capabilities from the images in robot scenario, robotic navigation scenario, or robotic pick and place kind of scenarios, that is referred to as robotic vision. So they differ very based on the application or the various on the kind of processing we place of processing we perform. Now, of course, all have the same algorithmic developments, and algorithmic development wise, they are all part of computer vision, we can consider. So here is an example where the fishes are coming on a conveyor belt, and then we want to classify these fishes into two categories. Okay, assume that we want to do automate this process. And then if you want to perform this, what do you think are the first tasks we should do? Again, the same question. So this kind of thinking will help us to understand the computer vision task in general on how they are developed. So if you want to perform a automated task of computer vision or inference from images, making inference from images, what should we do or how should we approach? That kind of thinking we should be able to develop through these examples. So what do you think is the first thing that we should do? The fishes are coming on a conveyor belt. Okay, and then we have two baskets. Assume that this is somewhere two baskets, this may be one basket. Okay, and then we want to put one of the class samples of fishes here. Okay, another fishes somewhere else. They can go further on the conveyor belt. Assume that that is the scenario we have. What do you think is the first thing to automate this process? We assume that there are two kinds, sea bass and Solomon fishes. So one can be sea bass and one can be Solomon. Okay, fishes. Maybe Solomon and sea bass. I am not very sure on that. But we would like to put these two categories of fishes differ in terms of length, they differ in terms of intensity variations and so on. So there are some variations that we can, with which we can make out the classification of these two fishes in addition to the taste. So now what do you think is the first thing that we should take care while making this computer vision task? Yeah, what should we start with? Shall we directly infer from the image, from this image, and then say that this fish belongs to that, this fish belongs to this category, and so on?
Find the edges.
Okay, fine, good, very good. We found the edges, assume that. Then what is the next task?
From the edges, we extract features like what is the length of it, what's the color of it,
Okay.
something like that.
Good. So the problem here is, assume that we have found somehow the edges. Okay. So the problem here is, say this fish is like this fish is like this, and so on. After finding edges, do you think anything else need to be done to find out, to measure the length? See, if I give a, if I have an automated algorithm to measure the length, and that measures the length as say the rectangular bounding box it puts for measuring the length. Okay, and then this is the length, and I say that this is the width. Is that fine?
We may need to consider the angle it is in also.
Right.
Depending on
So we should either align it or we should see the orientation of the sample. Okay, so first of all, we have to separate this fish versus this fish. Otherwise, what will happen when we want to directly measure the length? Okay, it is not that measurements will be wrong. So the process of separating one fish from other or one object from other is referred to as segmentation. Okay, so segmentation is essentially separating the objects of interest. Once we segment the objects of interest, then what do? We need to measure some kind of features. Okay, features may be length, intensity, average intensity values, and so on. So the separating the objects or any, see, this fish maybe say some completely wrongly aligned. So aligning the object or intensity variation sometimes may be important to be taken care of. So here assume that I have put a camera such that it is very bright here, okay, and then it is very dark here. So in that case, what happens? My measurements of the intensity over the sample will not be accurate. So I have to first correct that intensity variations, okay, and then make my measurements. So all that comes under pre-processing. So here in particular, in pre-processing here, it can be say segmentation. Okay, and then what else? Alignment. Okay, and then what else?
Intensity adjustment.
Yeah, intensity or contrast adjustments. It is also if contrast means, see, in some cases the black to white region may be very close, in the sense that the we may not be using all 0 to 255 intensity ranges to capture the details of the image. So my region itself is dark, and then my light there is itself is dark. So the captured image may be in 0 to 50 itself, pixels itself. In such case, I will not be able to get good assessment in terms of the inference. So I may need to enhance the contrast. So intensity or contrast enhancements to be taken care of. Okay, so once we take this, this roughly are pre-processing here. After that, what we need to do? We need to make some measurements. What kind of features?
Sir, I have a doubt.
Yeah, ask.
So if the fish is far away in the picture, like it is zoomed out, then the original length is different from the measured length, right?
Yes, correct.
How do we handle that?
Yeah. So here, if the problem is just putting the fishes into two different categories, it is good enough if the camera, okay, to the conveyor belt region where we are the fishes are, that distance is constant roughly, in sense that say if the conveyor belt itself is not very inclined, so we assume that the fishes are roughly at the same distance from the camera. That is good enough. But if there is a very if the camera is very close, the distance to camera to the conveyor belt is very small, and then there is a nice variation or big variation in the conveyor belt, then what happens? The scale variations occur because of the projection of these 3D samples onto the 2D image. Okay, in such case, we have to take care of the scale variations as well.
Sir, will this video be posted, sir? I'm having current and bandwidth issues.
Yeah, sure.
Thank you, sir.
Yeah.
So we assume that the scale is constant.
Yes. In this
Okay.
example, we are assuming scale is constant. So
Okay, thank you.
yeah, but however, if that is not, usually if the camera to the object distance is far away, okay, and if all the objects are of same distance, roughly same distance compared to the camera, then scale variations we need not bother. However, say if we are imaging from CCTV camera and some person is very close to it and some person is very far, okay, we can't measure the height of the person from image. We have to take care of the absolute distance of the person from the camera to measure the size of the height of the person and so on. Same is the case in any application.
Okay, sir.
Yeah, fine, good. So what kind of features can we measure here is the next question. What kind of features do you think we can measure? Anyway, height is one thing. Height, okay, and width. Okay, and what else? See, if you want to measure intensity here, see the sample is this much. You can see that the sample is varying from say some over a big region from here to here, whatever. In that case, what intensity do we take as the measurement, okay, of intensity for that fish? So there should be some quantification like average intensity measurements or some, okay, so we should identify the tail and the head, okay, and then in different regions, how much is the intensity? Some kind of such measurements has to be taken. So some quantification on the average intensity measurements. See, the problem here is that, so here this is the fish classification. Tomorrow we may be interested in face recognition. Okay, do you think same kind of features or same kind of processing, pre-processing is good enough for that? So I want to measure the face, different faces I want to differently identify or recognize. Okay, do you think again I will measure the same features? Yes or no?
You may not.
Yeah, we may not. The reason being is, say, if it is completely different problem, for example, red blood cells and white blood cells we want to classify. Okay, then do you think still I will go with the same features? We may not go. So sometimes the features of interest may may be common across different tasks, but in general, it is driven by the application of interest. Different features are required in different applications. And similarly, the pre-processing also varies from the application to application.